Much database.
Can people hear me okay? Cool. Great. Hi, everyone. I'm Rayna Rampalli. I'm a fourth-year grad student at Dartmouth. I'm here on behalf of the Wrinkles in Time collaboration, where I'll be talking a little bit about the work we've been doing to trace spiral arm passages using gyrochronology. And I'll just shout out our team very quickly, but we'll get right into it. So this collaboration really came together as a result of this plot that Wilma Trick published back in 2019. So she took about 3.5 million stars from Gaia DR2, calculated their actions, and then presented them as such. And so what you see here are stars as a function of their angular momentum in the z direction on the x-axis versus the square root of their radial action on the y-axis. And what these action coordinates more intuitively map to are essentially the orbital size the star has as it moves about the Milky Way versus the eccentricity of that orbit. And so you can see the population of stars here in action space. There's these interesting substructures that start to pop out in action space. And so she's highlighted what those are on the right-hand side. At near circular orbits, so down below, you have these known moving groups she's identified in ovals. And then as you jump up to more eccentric orbits, you have these ridge-like overdensities, and these are what we call wrinkles. And based on work we've done within the collaboration, based on stuff that's been discussed in literature, we think these wrinkles are actually kind of the kinematic substructures that have been left behind by spiral arm resonances. So essentially, a spiral arm will pass through a region and kinematically heat stars from these near circular orbits up to these more eccentric orbits. And so this is really exciting because, this has been discussed in simulations, but we're now seeing observational evidence of this. So we can go ahead and study those observational signatures and kind of lend some insight into what's going on with spiral arms. And so the main kind of motivating question for us is, when did these spiral arm passages happen to leave these wrinkles that we can now study? And so the way we approach this is really with a stellar age distribution kind of analysis. So we choose this kind of mode of trying to understand things because we know that stars are born usually on near circular orbits. So they're going to sit somewhere down here in galactic action space. And then only over the lifetime of the star does it kind of move up in terms of orbital eccentricity, as it's had more and more time to be exposed to different kind of slow-acting dynamical phenomena and end up in these eccentric orbits. So these wrinkles are located in a very dynamically old region of phase space. And so on first pass, you might think that when looking at the ages of stars in wrinkles, they should be largely old. And that's certainly what I thought. Turns out that's not the entire story. So the first kind of results from this group were really provided by Amy Smock. She's a grad student at University of Arizona and did a lot of simulation work to understand where stars are sitting, pre-resonance event and what happens post-resonance event. And so this is kind of the big result from her work, which will be coming out in a paper soon, where you see a simulated wrinkle. You have the stars and where they sit in action space pre-resonance event, and then they've been colored by where they'll move in eccentricity space post-resonance event. And so what's important to note here is if you have a young star sitting at a near circular orbit, so somewhere down there, after this spiral arm passage or this spiral arm resonance, it's going to jump up and increase its eccentric orbit. And so what this implies for when we're looking at ages of stars and wrinkles is that we're not only going to see old stars, which is expected, we might see quite a few young stars as well. And so we can test this hypothesis using observations, and we do so using TESS and gyrochronology. So, TESS is kind of the natural photometric complement to Gaia. Gyrochronology makes sense given we can measure rotation periods with TESS. There's certainly a number of caveats with gyrochronology, as we may all know, but a lot of those caveats work to our advantage here because we're really interested in the young stars that are present in these wrinkles. And the reason this is the case is because these young stars, again, are not typically at these orbits, right? They're born on these near circular orbits, and they can't be born in wrinkles. They've had to be kinematically heated to these eccentric orbits as the wrinkles are forming. So if we find young stars in wrinkles, that is letting us place an upper limit timestamp on when the spiral arm passage happened that created this wrinkle that we're studying. So just to walk through that maybe a little more explicitly, let's say we've observed this wrinkle on the right here. We have my little red star. We measure a rotational age of about 120 million years. What that means is that the spiral arm passage that has created this wrinkle happened no more than 120 million years ago. And so that's really kind of the underlying reasoning behind, what we're trying to do here when we kind of move to the observational side of things. And so that's what we've done. We've started by updating the data. Wilma's work was done with Gaia DR2. So we update our actions using Gaia DR3, use RVs from more calibrated and more precise surveys like Gala and Apogee. And this is the following action plot that we get. So things look very similar. We still have those wrinkle-like substructures here. So everything's looking great. We then want to actually select the wrinkles. So this is something Wilma mostly did by eye. So we were kind of interested in leveling that up a bit and choosing things using, computational methods. So some sort of clustering algorithm. This is, again, something Amy is leading. It's proven to be a little bit difficult because we're looking for, these ridge-like overdensities. So, looking for certain structures with our clusters. But we've had some luck literally in the last week and a half, thanks to a colleague at Dartmouth, Emily Boudreau, who looked for clusters in where we would expect to find wrinkles. And these are the clusters they find, which look wrinkle-like, at least in my opinion. So we've had some luck in the last few weeks. And so this is very promising, but certainly an active area of work. So kind of simultaneously, we've also been taking on the task of measuring rotation for TESS, which a lot of us know has been quite difficult. This is something I've worked on the last couple of years of graduate school, and last year published a pipeline that was semi-automated in nature. This is the kind of different elements of the pipeline. And since Isabel Coleman's work earlier this year, been inspired to fully automate the pipeline using a random forest classifier. So I've just thrown this up here. I won't walk through it, but if anyone has any questions, let me know. Rest assured, we've tested this pipeline on a number of stars in benchmark clusters, as well as stars in high action space, and we get about an 80 to 90% recovery rate. So things are looking pretty good. So then we kind of move on to doing the real exciting part of this, looking and seeing what things rotationally look like, in wrinkles and not. And so because we're still working on the wrinkle finder, we don't explicitly look for rotation signatures in the wrinkles. Rather, what we do is just see what's going on rotationally in all of high action space. So this is the area we explore. So looking at stars with a root radial action greater than 8. This ends up being about 10,000 stars in TESS that have light curves. And so we go ahead and apply my pipeline to this, get rotation periods and respective gyro ages for these stars, and see what's going on. And so we'll go ahead and show you the results. When I first saw this, I was a little confused given the hypothesis that Amy's work showed, right? That kind of suggests that, young stars should maybe almost exclusively be in these wrinkles. And we see there are certainly young stars in wrinkles, but they're elsewhere as well. And so this is something we see with, rotation. Is this something we see with other age dating methods? The answer is yes. So we also kind of throwing it back to yesterday's lithium session, we have a number of stars that had Galah lithium equivalent widths, so we're able to get lithium-based ages as well. And we kind of see the same thing. So we see lithium-enriched stars both in wrinkles and outside of wrinkles. And so the implications here are that the spiral arm resonance theory is certainly at play in that we're finding what look to be young stars in wrinkles, but there's clearly other dynamics at play as well that are kind of moving stars into these eccentric orbits, maybe somewhat more stochastically. And so this kind of just, we are kind of in a place where we have more questions than maybe we started with, but that's great, it's exciting. And so we can ask the question of what are these, dynamical phenomena? How do we figure out what they are and kind of go from there? And with that, I'll just summarize by saying this is super exciting. We get to apply gyrochronology for galactic dynamics applications. And we're doing so combining a bunch of survey data. And yeah, as I said in the last slide, we find rapid rotators and lithium-enriched stars in these eccentric orbits, which are, unique because we're finding young stars in these dynamically old regions. And there's a number of reasons why this is happening. I've focused on the kind of spiral arm passage source, but there's clearly other things at play. And so we're really excited to figure out what those are. So thank you, and I'll take any questions.
University of Florida. So there are two sequences. There's slow sequence of slow rotators and fast rotators. How do you separate out young stars that intrinsically rotate fast from old rapid?
Yeah, so we haven't kind of gotten, or I should summarize. Okay, so the question is, you have the slow rotation sequence and the rapid rotation sequence. Have you separated those out here? And the answer is no, not yet. We're kind of just doing a first pass to see like rotationally what's going on. And is this something we see with other, age dating methods? And the answer is consistently we're seeing what look to be young stars, whether it's with lithium or, gyrochronology. So we're not quite there yet, but yes, we would do a deeper dive after.
Steve Sauer, CFA. What are you calling young?
Yeah, so the question is, what are you calling young? So typically at these kind of dynamically old regions, we don't expect to see anything, less than 2 billion years. We're kind of using like gyrochronology standards for young. So anything that has a rotation period, we can get a gyro age for. So, right now it's around 2 billion years, right? So although Lucy will be talking about that being changed tomorrow, but I think, anything less than 2 billion years is what we're calling young at this point.
In that case, do you include K stars in this?
Yes. So yes, the question was, do you include K stars? Yes, there's this issue of stalling and everything, but we're really using these ages as kind of upper limit timestamps. So regardless of what age the K star actually is, like finding one that is, 650 million years old or 2 billion years old is still informative to us. But once we kind of get into the nitty gritty, yeah, maybe I think the plan is to focus more on, the sun-like stars where things are better calibrated.
You want me to open? Yeah. Other way around? No, no. How's it going? Can you hear me? Louder? Higher? What if I yell? Can you hear me? It's good. Okay.